Okay, friends and neighbors, we're back and we're talking about curvilinear motion again, but this time we're talking about on a parabolic path. What happens when I have my object moving around a curved path, but the curve is not just, the radius of the curve is XYZ. This time the radius of the curve is constantly changing. It's parabolic. What? Well, we're going to have to do a few things different. Let's see what this problem says. So if the car passes point A with a speed of 20 meters per second. So here's point A, and it's going up this hill, right? And begins to increase its speed at a constant rate of 0.5 meters per second. So now number one, that's good, right? It says constant acceleration. So what does that mean? We can go back to our old equations. Remember our old equations here for constant acceleration. So if we want to find, I don't know, velocity at a time, now remember where these equations came from. If you don't, you can go back and watch the videos right before this. But all of these equations here are valid when we're using constant acceleration. That's what the little c over there on acceleration is. It's constant. So those are good. We'll use those, right? Determine the magnitude of the car's acceleration when s equals 100 meters. Now s is the arc length. It's the curve along that arc there. And when x equals 0. So when x equals 0, he's like there, right? That's the point where x equals 0. So let's see if we can figure this out, huh? So first thing, you know that I didn't write that. One of my students came in here and spent time and wrote this properly for me. So you'll have a fantastic experience. Does it make your time better here? Okay, let's find the velocity at point, I don't know, point C. Let's call point C over here where we're getting to when we at the very end there. So at that point, let's find the velocity. So I'm going to use this equation here. Okay. So I'm looking for v. Do I know v naught, which is the velocity when it first started out? Well, it said if the car passes point A and the velocity is 20, so that's the first velocity I have. So let's do a 20 meters per second, and let's square that. Oh, we got to square there too, don't we? Right? Plus 2 times the acceleration. The acceleration is constant, right? And the acceleration is 0.5 meters per second squared. So let's put that right there, 0.5 meters per second squared. And then we've got, what was S? Do you remember? S is speed. No. No. It's just position, right? So the original position, let's call the original position 0. So S naught would be 0. And S would be our final position. And they tell us that the final position is 100 meters. So, this whole thing over here is going to be 100 minus 0. All right, what do we need now? Our calculator, right? 20 squared is 400. And, 2 times a half, what's that? That's 1. And 1 times 100 is still 100. So this is 500 on this side equals to v squared. And so v is equal to, handy dandy calculator, is 500, enter, and then square root of that is 22.36. And that's meters per second. So that is the velocity when this guy gets over here 100. Okay, that's where the velocity is. Now, wow, the next part is just going to get a little bit mind-blowing. So how do I find, so they want us to find, what do they want us to find? They want us to find the magnitude of the car's acceleration. Okay, so we go back to the last video. You remember acceleration equations. So we have two things. We have tangential acceleration, we have normal acceleration, and then we have, I don't know, the magnitude of those two, or we could call it R for resultant acceleration, okay? Tangential acceleration, so the car is going around the curve and it's accelerating like tangential. Do we know what that value is? Matter of fact, we do, and it's constant. It's right there. The tangential acceleration at any point is going to be 0.5 meters per second. squared. So this is 0.5 meters per second squared. This is the tricky one. Okay, remember we had an equation for this, and it was v squared over rho. Now, rho in the last problem, we just had a round curve, right? And we had some radius. It was pretty easy to come up with. But on this one, I don't know, the radius of curvature is hard. It's so hard that it kind of blew my mind a little bit. I had to do a little extra thinking on this one. We have to go all the way back to calculus. And in calculus, y'all derived, you maybe not remember this, but you should have derived a radius of a curvature equation using calculus. So what happens is if you think about, like, this is one point on the curve and this is another point on the curve, and I have some gigantic circle. It's so big I can't even put it on my board, right? I mean, it's humongous, right? To the middle of that circle, right, somewhere over there is the center of this circle, okay? Now, if I have a big, gigantic circle, I mean, this is a big circle, right? Like, I don't know, 3 football fields across, right? That's American football. That other stuff's called soccer. What happens is you have little bitty segments, okay? And if you think about, like, this little piece of that segment over there, right? Look, you call this right here d theta, right? If you think about the little bitty segments, as the radius gets really big and d theta gets really small, those little segments are just straight lines, aren't they? It's like breaking a circle up into a whole bunch of little straight lines. And that's what this equation here does. It approximates from here to here as kind of an average and calls that, let's just be a straight line. And what happens is as d theta gets small, that straight line, it goes to 0. There's no error there, okay? And so I'm not going to derive this equation for you. You can look it up if you want to. Go on Wikipedia and look this up, radius of curvature. It's all derived there. You should have done that before. But this is equation for calculating radius of curvature when you have some kind of a function for your path. Okay, so this is something you got to remember. So when you have some kind of crazy function for your path, that's how you calculate the radius of curvature. Now v squared, we already know that, don't we? V squared is right there, or v rather. Velocity is right here. So the only thing that we need to calculate is rho, the radius of curvature. And let's use this. Now in this equation is 2 things, y prime and y double prime. This is the first derivative of y with respect to x. This is the second derivative of y with respect to x. Now we have an equation or a function right here for y with respect to x. So what we're going to do is, let's do this right quick. Let's do this. Y prime is equal to what, right? So I'm going to take the derivative of this function one time, and that's going to be what? Constants go away. This guy here is going to be 2 times 1 over 625 times x. So we can call that negative 2 over 165 x squared. Couldn't we? No, not x squared, just x. Sorry, remember we reduce our exponent there. Okay? Remember this? And now let's go ahead and do what? Second derivative, right? The second derivative, y double prime is equal to, what is that going to be? Let's change that. Well, it doesn't matter. Y double prime is what? Just this, right? What is that? 2 divided by, oh, clear. 2 divided by 165 is equal to, no, that can't be right. Oh, it's not 165, it's 625. No wonder I was, sorry y'all. I know you're like, hey, you're shouting at me, right? How about 2 divided by 625? 0.0032. So this guy here is negative 0.0032x. This guy y double prime is the derivative of that is just negative 0.0032. Okay, Let's plug that into this equation here and see what we get for r, for our radius of curvature, which we're going to call rho. Okay, so r is equal to the absolute value of 1 plus, let's just do 1 net minus, let's do that, plus what? That, negative 0.0032x all squared, and then that whole thing is to the 3/2, and then what? Divided by y double prime, which is just negative 0.0032. Now, what is x for this problem? Find the car's acceleration when s is 100 and x equals 0. So if I put a 0 in there, then this whole term is just going to be 0. So I'm left with 1 divided by 0.0032. And notice it's the magnitude of that. It's the absolute value. And so 1 divided by the answer is equal to 312.5. So that would be the radius of our gigantic circle. It's 312 meters. That's pretty big, right? So let's go back up here and let's see if we can get normal. Normal is, let's see what, v squared, which is 22.36. 22.36 squared divided by the radius of curvature, which is 312.5. This one's meters, that one's meters per second, right? And let's see what that gives me. 22.36 squared divided by 312.5 is equal to 1.60. So the normal AN equals 1.60 meters per second squared. So now I know the tangential, I know the normal. So how do I find the resultant of those two? Right, so the car over here, right, as the car's going around, this guy is 0.5, this guy is 1.60. So what I'm looking for is that guy. That's the resultant of those two. So the resultant acceleration, which is right here what they want, the magnitude of the car's acceleration, that's what we're looking for, is, remember it's the square root of the squares, Pythagorean's theorem. 0.5 squared plus 1.60 squared square root, right? So squared plus 0.5 squared equals second square root of the answer equals 1.68. 1.68 meters per second squared. That is the magnitude of the resultant acceleration. So there you go. Y'all keep asking me to, everyone, you're doing the easy ones. Where's the hard ones? That's pretty hard. We have to remember some calculus here in order to come back and solve this. Now this is the same stuff once we get that, once we figure out what that radius of curvature is. But beyond that, there you go. That's how you do it. All right, see you next time.